Let's rewind the clock and look at the history of the universe in our attempt of understanding cosmology, the past. In the beginning, well, not the beginning, but the beginning of when we started looking into the beginning of the universe, we start with Albert Einstein, who published his theory of general relativity in 1915. In this report, he formulated some equations that predicted that the universe was not static, as it was originally believed to be. It was either expanding or contracting. But there was some pushback to this idea. Newton had declared that the universe was infinite and static. It couldn't be expanding or contracting. It's exactly the size it is, and it will remain so forever. But as it turns out, Einstein's observations didn't actually contradict Newton's claims, so he did what anyone would do, just added what's now called the cosmological constant to fix his equations. But then came Milton Humason and his colleague Edwin Hubble, both of whom happened to be contemporaries of Einstein's and many other modern physicists of the early 20th century. In fact, if you'll allow for a quick little detour into physics history, Albert A. Michelson was one half of the famous Michelson-Morley experiment, which led to the eventual discovery of the speed of light, despite Michelson and Morley failing in their original experimental goal of detecting and analyzing the luminiferous ether, a substance that they believed to exist as the medium of the space between the stars, which allowed for light to travel within it. But as it turns out, there is no luminiferous ether, and light doesn't actually need a medium to travel through, even if it's coming from very distant galaxies. So together, Humason and Hubble observed over 600 distant galaxies. They determined that these galaxies are really far away and are continuing to move away from us. In fact, they always have been. The more distant the galaxy, the faster it's moving away. But how did they figure this out? By looking at and analyzing the spectra of these galaxies. Observing the apparent shift in the position of a particular spectral line yields the galaxy's radial velocity. In other words, they utilized the Doppler shift. If we look at this particular spectral line highlighted in the spectrum of NGC 221, we can see its position change as we look for it in the spectra of 4 other galaxies: NGC 4473, NGC 379, a galaxy in the Ursa Major cluster, and another galaxy in the Gemini cluster. Notice how in each new spectrum, the spectral line we pointed out originally has shifted quite a bit, and the radial velocity of each galaxy has subsequently increased as each new spectrum appeared. Now, radial velocity is the term used for velocity of an object as it moves towards or away from the observer radially, or along the observer's line of sight. Now, a quick but specific Google search for Hubble and Humason's work will lead you to the archived digital PDF copy of Humason's original publication from 1936, currently hosted on NASA's Astrophysics Data System Digital Library. A closer look at the document shows the original version of the spectra we were just discussing. However, a few things to note are the labels. Humason labeled the last 2 items as nebulae in their respective clusters, since it was not yet certain whether these were galaxies or nebulae, but that would be clarified later. He also noted in the text beneath the figure that the pictures of each galaxy, depicted in inverted color, were taken using the same scale and approximately the same exposure times, illustrating the apparent sizes of each galaxy relative to one another. They appeared to be decreasing in apparent size as the distances increased. And this would make sense. The further away something is, the smaller it'll appear. So when Hubble and Humason graphed the distances of these galaxies against their recessional velocities, they ended up with a very interesting plot. The data points, each representing an individual galaxy, seemed to follow the general pattern of a regular old diagonal line. Mathematically speaking, Hubble and Humason had produced a linear graph, which showed that the more distant the galaxy, the faster it was moving away. For example, this galaxy is located at a distance of about 157 megaparsecs, or 157 million parsecs, and its radial velocity is about 7,500 kilometers per second. This idea that galaxies are moving away from us and their recessional velocity depends on their distance is called the Hubble law, despite it resulting from the combined efforts of Hubble and Humason. So if further galaxies move away from us at faster speeds, closer galaxies must be moving away from us at slower speeds. For example, this galaxy is about 84 megaparsecs away, and it's also moving away from us too, but slower, with a radial velocity of about 4,200 kilometers per second. Now, Hubble and Humason's work showed that distant galaxies are moving away from us, and the further away they are, the faster they go. But here's the catch. These distant galaxies aren't moving through space. Space itself is expanding. Now let's try to make some sense of this. Think, for example, of raisin bread, or chocolate chip cookies if you don't like raisin bread. When the bread rises as it bakes, the raisins in the dough begin to move away from each other as the space between them increases. But we don't see raisins in the universe. We see light. Specifically, we see waves of light. Now, if you don't like raisin bread or cookies, you're in luck, because our next example focuses primarily on waves of light. Think of a rubber band with a squiggly wave drawn onto it. The wave has some original wavelength of some original value. Now, if the rubber band is stretched, so is the wave that's drawn on it. The medium in which this wave exists is stretching, and therefore so is the wave itself. Upon expanding, its original wavelength increases to the new stretched or redshifted wavelength. Another way to look at the expansion of the universe is through the balloon example. If you had a balloon with a wave drawn onto it and some grid lines too, inflating this balloon would show the stretching of the wavelength as it's inflated. The more the stretch, the redder the wavelength becomes. When waves of light are stretched in space, they're stretched because the space itself, within which the photons of light exist, is stretching. This type of redshift is called cosmological redshift. Now, you may be asking yourselves, what in the world is cosmological redshift? Well, since the Big Bang, the physical space of the universe has been expanding. While stars and galaxies might be able to maintain their size, the space between them grows. This results in wavelengths that may have originally been short and blue to also grow larger with the expansion of space, becoming longer and redder as space expands. The motion of these galaxies, as they move apart from one another due to this expansion, is called the Hubble flow. Hubble used an earlier version of the graph we were examining just a few minutes ago to measure this expansion rate by finding the slope of this diagonal line. As is the case with any straight line, we can use the equation y equals mx plus b to find the slope. But don't worry, we're not jumping headfirst into any algebra today. We're just looking for the slope, m. So maybe we're just going to be dipping our feet into a little bit of algebra. Now, you may remember the phrase rise over run from earlier math classes as one of the definitions for slope. If this is new to you, we'll break it down right now. Let's say we want to find the slope of a line drawn from the origin of the graph to this point. We draw the line starting at the origin, at the 0, 0 point, where the value for both horizontal and vertical coordinates are 0, and connect that point to the point in question. The amount of vertical rise here is 7,500, and the horizontal run is 157. To find the slope of this line, we divide the rise by the run, which gives us 7,500 divided by 157, which is about 48. We can do this again for this point. Again, we draw a diagonal line connecting the origin of the graph to the point, and we determine our values for rise and run. Here, the vertical rise is 4,200, and the horizontal run is 84, making our slope 4,200 divided by 84, which is exactly 50. Now, we can continue to do this for this point, and this point, and this point, and this point, and even this point, and in fact, all the points in the graph, or we can just find the slope of the trend line, which was already provided for us in this case. In cases where the trend line isn't provided, it can be determined by analyzing the data points, and usually computer programs like Microsoft Excel or Numbers on a MacBook or Google Sheets are good for doing just that. But since we have it here, we can just find the slope of the trend line, and we find that it's, in this case, 67. Now, it happens to be labeled a capital H here for the fact that the slope of this specific trend line on this specific graph, comparing the recessional velocities of galaxies to their distances, is specifically the Hubble constant because it's the slope of the Hubble law. Its value is currently estimated to be closer to 67.80 plus minus 0.77 kilometers per second per megaparsec of distance, according to the most recent data from the Planck mission. This implies that for any two galaxies located 1 megaparsec apart, the speed of the further galaxy would be about 67.8 kilometers per second faster than the closer one.